And try to I want to have.
And then now you go back to what.
Yeah, no, I just do whatever I'm spraying.
Welcome to this installment of Math Club.
Where
I am very pleased, introducing, Hazel Torek, who is going to tell us about interactive theorem proving in Lean.
Hi, everybody. I'm here to talk about Lean, which is a proof assistant tool, basically using computers to verify theorem zero. So what I'm going to go over, I'm going to talk about what automated or interactive theorem provers are, what they do. I'm going to talk about the Lean programming language, which is a specific theorem proving tool. And I'm going to demonstrate what the code for that looks like, and I'm going to spend, I think, most of my time on how they actually work under the hood. So this is kind of an introduction and motivation for why it's useful. So as mathematicians, we all write proofs, and a big part of that is making sure that your findings are correct, going through step by step and just verifying everything you found. But sometimes it can be more difficult to identify possible issues if they're more subtle. Even if you show it to other people, you can have other people check it, but sometimes it's a really subtle issue. It's easy for things to slip under the radar or for people to take a while to figure it out. So just how we like use computers to check that we do arithmetic correctly, we can also use them to check that we do our proofs correctly using interactive theorem prover tools. So kind of an overview of what they actually do. If you write a proof that you come up with in the syntax in the programming language for this specific theorem prover, it will verify it each, like, kind of step by step, go through it and check that your logic makes sense through every step. It does not come up with the proof for you. It kind of sounds like that, but unfortunately no.
Are you kidding? I'd be out of a job.
I know, yeah, it'd be devastating. Practically, there's not that much significance to it now. It's not really that widespread of a practice. There's a lot of mathematicians who advocate for their adoption and use them personally, but it's not really something you see all that often at all. So maybe not as much for practical use, but the way they work uses a lot of interesting math. You can also use them in things other than just proving and formalizing mathematics. Formal verification, for example, is using computational methods to prove that your hardware or software that you've written has certain properties. So we can prove things about computer programs the same way we can about mathematical statements. Another reason this could be possibly important, it could make it easier for large groups of people to collaborate on that. If you send like an overleaf document to 300 people and try to have them all work on the same thing, it's going to be kind of a mess and kind of disgusting, and nothing's going to get done. But since we have tools specifically for working on like version control tools for collaboration with code, it could be way more easy for people to work together on formalizing things in Lean, what they're doing now. So in a second, I'm going to get into some examples of using it and what that looks like actually. But before I do, it's kind of a brief introduction to what we're going to see. Lean will always display the active objects in your statement, your hypotheses that you have, and the goal that you're trying to prove. We have different tactics that we can use to establish different types of proofs or perform different types of reasoning. We have different tactics for doing induction or for doing contraposition, et cetera, so forth. Heather Macbeth, which in her book, The Mechanics of Proof, which is a textbook for a course kind of like 3190, but focuses on formalizing proofs in Lean as well as like normally writing them out. She said the tactics each constitute a single permissible atom of reasoning. So a single kind of individual step you can take. So to show you guys what this looks like, I opened the wrong folder. Awesome. Okay. So this is, can we read this? Is that big enough? Okay. like beforehand. This is what the code is going to look like when we're actually programming it. So I've got some very simple to building up to a little more complicated examples here. Right on the board, and we're going to talk about how we prove it kind of normally and how we would prove them in. Okay, so my first proof: let x and y be natural numbers. Then you guys, this is going to be a really crazy one. 37x plus y equals 37x plus y. Can anybody explain to me why this is true without using the word trivial? Give me like a one word. Reflexivity, that's the word I'm looking for. Equalities and equivalence relation. We have reflexivity. If I have the same things on both sides of the equal sign, it's going to be true. So kind of like how we do normally, we just say RFL. This is the tactic. Like I said, we have tactic for establishing different kinds of reasoning. RFL we use when we want to show something's true by reflexivity, when we have the same thing on both sides of the equal sign. We can see here up above that, we kind of declare the first steps of the proof, like how we normally, when we start with a proof, we have a statement like this, like declaring your variables that you're going to use. Right here, we do kind of the same thing, just to do the syntax here. We say x and y are natural numbers. And then here next to that, we write out the actual statement we're trying to prove. And then we say by, and then we explain how we're going to do that. We use the tactics that we want to use. Another example that I did right there. Let A and B be rational numbers such that A times B is 1 and A minus B is 4. And then what we want to prove is that A plus B squared equals 20. Well, so we would normally do this by breaking this apart and doing each calculation. So, for this, let's say A plus B squared equals 4AB. A minus B squared plus 4AB. We can do that. And then we have an A minus B, which we assume to be 4. And we have a 4AB, which we assume to be 1. So that's 16 plus 4, that's 20. So what we said is true. So now we're going to go through the same steps over here in Lean. So, like before, we declare our numbers that we're going to use as examples, our variables. And now what we've changed in this step is that we have our hypotheses. I said assume that A minus B is 4 and assume that A times B is 1. So we declare these as hypotheses here and we label them H1 and H2. And then like before, we just give the statement that we're trying to prove as well. And now we're going to use a different tactic here because the way we perform this proof is different from the way we perform that proof. What we're doing here is we're using the calc tactic, which is basically short for kind of proof by calculation is what Heather Macbeth calls it in that book I mentioned earlier, where you're kind of just making a chain of equalities like we did, and then just taking the first thing and the last thing and saying that's why it's equal, right? So we say A plus B squared, A minus B squared plus 4AB. We have to explain why that's true. In this case, we can do that because we're in a ring and that's allowed. Same thing here, the underscore is just the same as if I had started this line with this thing. It's just saying keep moving from the next line. So we're building a chain of equalities. So we get from A plus B squared to here using our hypotheses in this step. And then we just finish by adding these together and doing the numbers, and that finishes the proof. Oh, awesome, it finally loaded. So now we can see what I was talking about earlier. I said that lean shows. Why is that wrong? Lean shows all the objects we have at every step of a proof. Like here we can see A and B are rational numbers. It also shows the hypotheses we have, like I said, A minus B is 4, A times B is 1. And it also will show the goal we're trying to prove, which in the last example, 37x plus y is 37x plus y. So, and after each step, this updates in real time. So now my cursor's before I use the RFL tactic here. We can see once I go after it, it says no goals. I just completed the proof and it's closed the goal. So I'm finished with that now. Yeah. Another example I'm gonna go through kind of briefly because this is a lot similar to the last one. If we have real numbers R and S, and we assume that S is equal to 3, and that R plus 2S is -1, we can prove that R is equal to -7. And we're going to do this in the same way by creating a chain of equalities that we can use. We can write this because we're in a ring, and then we can simplify using the hypotheses. All the numeric simplification, we can just use doing the ring tactic because that makes it easier than having to explain why 1 plus 1 is 2, etc. And I also have a set theory one here, which you guys probably all did something really similar to this when you took 3190 in the first couple of weeks. If I have 5 sets A, B, and C, and I assume that A is a subset of B and that B is a subset of C, I have an element X in A, and I want to prove that X is in C, right? So this is pretty simple, very easy. But it's a little different from what we've been doing before. We're not working with numbers anymore. Instead, we're working with sets. So we're going to use some different tactics to accomplish the goal here. So in this case, I can see we're just kind of doing the same thing. A, B, and C are sets that contain elements of type U. I'll get to that a little more later in the talk. My hypotheses are that A is a subset of B is a subset of C, and that X is an element of A. I want to prove that X is an element of C. Well, to start, I can just say we know that X is in B because A is a subset of B and X is in A, so then it has to be in B. And then we can say, we can finish the proof by saying, well, if B is a subset of C and X is in B, then X is automatically in C as well. So these are two different tactics than we've used before. The half tactic is when I add a hypothesis. So if we start up here, we can see I only have the hypotheses I declared here, H1, H2, and H3, which are the ones I wrote up here as well. So that's all I have at this step. But, and like I said, we can see our sets and our goal. After this step, where we say we have a new hypothesis that X is in B because of the first hypothesis and the third, we can see that now we've introduced a new one, H4, that says that X must be in B as well. And then we use that in combination with the fact that B is in C to close out our goal. So exact is the tactic you use to finish a proof by just applying the hypothesis. Actually write that in. And like I said before, Lean is also a programming language, so you can also program in this like you normally would in other programming languages. The syntax is weird, but it's still possible. But that's not really what we're talking about, so I don't have a lot of example on that. Okay, awesome. So, and if you thought that was interesting, or if you're interested in learning more about using Lean, there's also some really helpful resources you can use out there to learn. The first one is the natural number game. Why is it that bad? Awesome. Okay. Yeah, so this is the natural number game. And it's basically an introduction to proving things in Lean with some very basic proofs revolving around natural numbers. So we can see the first thing it starts you out with is, like I said, yeah, similar, just the same as the one we did. We just proved it by reflexivity. And as we go through these, the examples get more and more advanced. We apply hypotheses, we learn more tactics. And as you progress throughout this, you can move into different kinds of operations and different topics. So from the piano axioms, you build your theory of addition and multiplication, and you can also talk about some more advanced algorithms in Lean and proving inequalities as well. The other resource I mentioned here was, yeah, this book. This is the one I've mentioned already, Mechanics of Proof. So this is very similar to kind of like what you go through in Math 3190. We can see we've got like some simple proofs here. And this talks about both how you prove them normally just by writing it out on paper, and how you would prove it in Lean, how we formalize mathematics there as well. So it's kind of handling both of those topics. We can see we have an example here, and we can see the corresponding example here. This is the last one. This is more of a reference than like a tutorial, but this is mathematics in Lean. And basically for all your different kinds of fields of math you're interested in, it's got some tutorials focusing on those specifically as well. And we also, beyond learning, if you want to see like notable people and notable projects using Lean, there's an ongoing formalization project of Fermat's theorem, which is kind of a lot of work to have undertaken for like the first thing somebody did in this language, but it's still an ongoing project to formalize all the entirety of Weil's proof of Fermat's theorem using Lean. This is going to take a while. This is kind of huge.
So how does that work? If it depends on all these other papers, and it depends on the other papers. At some point you have to.
You have to cut. You kind of have to cut it off.
I guess.
I mean, yeah. So that's a good question. Part of it, I'm sure, is that they do have to go back through a lot of these papers and formalize a lot of stuff in Lean. But that's actually a really good question.
I mean, even basic things about like analytic number theory in a graduate course, you have to go. That's going to depend on analysis and algebra, and you got to go back to.
You have to go back, right? So one of the things that Lean has to kind of help address that is there's this kind of standard library of a lot of existing mathematical tools and theorems across a lot of different fields. This is called MathLib. If we go back here, actually, you can see this is where, you know where these comments are stupid. This is where I import my tactics from, and this is where I import like the different types I need from. And basically for all the different, there's a lot of different stuff already formalized in here, and people are contributing to this like as a community to kind of build upon it and make this more thorough. So this is probably like the starting point. People have been adding stuff to this, but for a lot of those papers, they probably did just go back in and build that into here, which is probably why, I don't know how long this has been going on actually, but it's probably part of why it's taking so long to do. Another notable project, this was started by Torek, who's a big advocate of actually using Lean. The equational theories project. So an algebraic magma is, for those of us in/having taken 4120 or an algebra class, it's like a group, but you lose associativity and identity and inverses. So basically, like there's nothing useful or good about it, and it's kind of disgusting. And the goal of this project is to map out all the implications between different equations we can state in algebraic magmas using using only up to 4 invocations of the actual operation. So we can see here all these stop ones we have 4. Because that's still this many different laws and this many different possible implications to explore between all of them. Just kind of a pretty big number. So I could not tell you why I could not tell you why he's doing this, but this is, I guess, kind of exploring the usage of Lean, and I think, yeah, you can see the actual code he's using to do it here as well. A lot of these have code on GitHub, like the Hermaz's Theorem one. We can see all of these are stored in different files, and a lot of different people are contributing to this. It's kind of a community project, which leads back into the thing I said earlier. When you have something that's kind of closer to a programming language than something like LaTeX or like how we normally do math, it can be a lot easier for larger groups of people to contribute to it because we have more fleshed out version control tools in the development of software that we use, like Git and GitHub. But going back to this, yeah. There's also other options than Lean. This is not the only interactive theorem proving tool out there. It's just the most widely used in formalizing mathematics right now. Most of these are less prominent, and I think they're like computer scientist things mostly. But there are other options that people still use to do math, just not as widespread as Lean. So now we're going to talk about how that actually works, which is going to be kind of a whole thing, and I'm going to hand wave everything in true computer scientist fashion. So if you have questions about that, you can just ask me later, because I don't think I have the time or mental fortitude to actually get into it all. Type systems, okay. We're going to do some math, guys. What's 1 plus 2? 4. Awesome. It's 4. What's 1 plus the string hello? 4. We don't really have a notion of a plus operation that makes this make sense. So when we're for those computer scientists among us, we can see, like in this screenshot I have here, most programming languages will prevent us from doing nonsense like that. Because we want to allow things that make sense, like 1 plus 2, but not 1 plus hello, because we just don't really, that doesn't make sense to us. So it's kind of something we have an intuition for already, but it's not something that we think about, I guess, as much. So like a similar kind of thought is if I have a vector in R3, and I have a vector in R2, I can't really add these in any like meaningful way. I can define an addition operation that does something with it, but like, why would you? It's not useful. So what we want to do is thinking in terms of Lean, in terms of programming languages, we want to disallow things that don't make sense, like 1 plus hello or this plus this, but we want to allow things that do make sense. We want to make sure that this evaluates how we expect, and we want to make sure that if you try to do this, it says, no, that's stupid, stop. Like we can see here, string can't be coerced into integer when you try to add. Same idea there. So the tool we have for doing that in programming languages is called type systems. So we use these to, in a colloquial sense, we verify that programs make sense. Because it doesn't really make sense to do something like this. So we assign each individual term, like I can take this to be a term, this to be a term. I'll say this is of type integer. I'll say this is of type string. I can say this is of type whatever. It doesn't, yeah. But we assign each term a type, and then we can go through and make sure that we're prohibiting operations between 2 types that don't have that operation defined between them. So we're gonna take that and we're gonna make it more mathy. Type theory is kind of what you get when you take that idea and instead of doing it in computers, you do it with math. You formalize kind of this notion of a type system. There's different examples of type theories, like the type lambda calculus and the calculus of inductive construction, not math 1080 calculus, dare I say. This is not the same as set theory for reasons that, to be completely honest, still kind of a little bit beyond me. It's still kind of arcane, but has to deal with this notion of computation. If I have a set like 3 + 3 and 6, we think of this as a set with one element, because these equal the same thing, but when we're dealing with types and type theory, because this originated with computing, we emphasize computation. We consider these 3 + 3 and 6 to be separate terms, but they compute to the same value, which gives you a lot more of a complicated notion of equality when you axiomatize it like this, but it gives you some useful things like we're going to talk about. So the Curry-Howard correspondence basically is how we get from what we just talked about to actually doing math. It's kind of the bridge between programming languages and type systems and formalizing actual mathematics. So one way to think of this is if I'm doing propositional logic, I can have two statements, P and Q. I can say P and Q, P or Q, not P. P implies Q. If I have types, as in a type system in computer science, A and B, I can combine these to have the product type A times B, which is like a Cartesian product with set. It's the set of pairs of elements from A and from B. I can have what we call that's the wrong thing. The sum type, which is either an element from A or an element from B. And we can have, that one's actually kind of gross, I'm not gonna get into it. But basically the idea is that this was discovered by Hazel Curry, who was a mathematician. He, in terms of the lambda calculus, he discovered that we kind of have a correspondence between terms in propositional logic and different types in terms of type theories and type systems. And this is kind of the key observation we're going to use to get from programming and programming languages to actually understanding how it checks our work when we do it. So the important part to understand here, what does that actually mean? In Lean, when we write a proposition, it gets encoded as a type. So like we saw when we had that, the goals and the hypotheses on the side here, we're storing that all as types. What we're doing is, because of the Curry-Howard correspondence, we can take any kind of mathematical statement we can write using propositional logic, and we'll write it using types, which we know we can compute with because that's kind of where they came from. We built them using this notion of computation. So because according to the Curry-Howard correspondence, if I want to prove a proposition, then I'm constructing a term of the type corresponding to that proposition. So each step of our proof, we're constructing a term satisfying the type corresponding to the mathematics for that set. So to kind of simplify that, basically, if I want to prove P and Q, like if I have P and Q that are logical statements, I need to think of it this way, provide evidence that P is true, and I need to provide evidence that Q is true. And then having those together, I can prove that P and Q is true. Same thing here, I can provide evidence that P is true or that Q is true. So instead of providing evidence that P and Q are true, we can just switch from here to here. We can think of that as proving that A is a type that is inhabited, that there are some values of type A that actually exist. and that there are some values of type B that actually exist. So to prove that this term is true, we want to prove that the corresponding type is inhabited, that I have a value of this type that can exist. So that's what I mean when I say to construct a term of that type. And the issue with this approach to kind of formalizing our mathematical statements in this way is that is the halting problem, which is kind of a big deal if you really think about it. But type inference and type checking a program, it's kind of like going through and symbolically evaluating a program, since we have to step through every possible branch of the program. And that is subject to the halting problem, because you're going through each branch of the program and checking that it returns a value of some type, or that basically that it will halt. So types checking systems, depending on how advanced they are, might not necessarily be decidable, which is kind of a problem. If you don't know whether it's actually going to sit there loading forever, or if it's actually ever going to end. But there are a lot of kind of more empirical ways to get around this. But yeah, that's all I have. Does anyone have any questions?
Any questions? Yes.
Actually, yeah, I have a question.
Yeah.
It was about the demonstration, because the first example we did, we had to tell the computer that equality is reflexive, and that sounds very, I guess, pedantic. But then the next group used the tactical ring, which it seems like we're just saying like, yeah, you can do that. So like, probably there's a lot going on. Like, can you unpack stuff for us? Like, what actually goes into making like a tactic like ring that can just do the things we think are true?
That's actually a really good question. I'm not gonna lie, I'm not sure if I have a good answer for that, honestly. This is something that I, as well, am relatively new as well. But
Oh, so I guess I'm wondering, like, is the idea that people have done all of the gritty details for us so that we don't have to, like,
kind of, yeah. I mean, in the same way that like if I want to publish like a mathematical paper, I'm probably gonna pull in, some like lemmas or theorems or other proofs from other people. The idea with things like Mathlib here is that we're kind of building this library of mathematics as a community, and we can kind of just, to make our proofs easier, instead of having to start like from the most basic instructions to prove anything. We have Mathlib to pull upon, which kind of gives us these tools already proved by other people. Does that make sense?
okay, yeah, I guess, and I'm also wondering, I don't know, like, it's unlikely that the exact like rewriting that you did like is hard coded somewhere. So how is the computer actually knowing how to verify that? Well, is it like, it's not AI, right? Is it like some clever?
That could honestly probably be its own cog. I don't know, honestly. I mean, there's a lot of different like existing methods for in computer science, like use a lot already in things like compilers and optimization. Like maybe I shouldn't get into this too much. There's a lot of different methods of like simplifying and rewriting expressions that we can use. Like, this is one I've been learning about recently, egraphs. If I have an expression that I want to optimize in some way, like here we have a times 2 divided by 2. We know that's a. We can kind of build an egraph that helps us represent different ways of writing equivalent programs that will represent the same value. So this is one like method that people might be using. I don't know how the actual rewriting works under the hood, but I guess there are. This is like one thing, I guess. Is that a satisfying answer? Yeah, okay. Yeah.
Yeah, just two things I'm thinking out loud, or, thinking out loud here, I don't know if you have a specific answer to this, but, I'm curious, we've also improved, but we're like, for 1 = 2 by dividing by 0 in a clever way. You can like trick this into doing, like how it handles things like that. That was one thing I was thinking of, and the other one is just curious, with calculus, how it handles differentials, and if it thinks dx, if it thinks dy dx is a fraction, or,
That seems.
I don't know if you know the answer to those. But
Yeah, I might. The first one, I kind of maybe, let me think. Like if I. Yeah. Wait, I don't think I forget what the tactic is for the, but basically, this is, I mean, yeah, so people, this is kind of the same idea as you used to prove by contradictionally. If I ever at any point have a hypothesis that is just something that's false that I can never reach, then I can just close out my goal because you can, if the hypothesis is false, if what I'm assuming is false, then I can prove whatever is it. Yeah, you just say trivial, and so does that answer the first question, you think?
Well, yeah. Can you ever trick it to say something like this is true? I don't know if you know
Yeah,
the
no,
thing
I
I'm
don't,
talking about, but you assume like A = B and then you square both sides and you multiply by.
Oh, like-
something.
okay,
Yeah, in fact, and you end up with 2 = 1.
right,
And
like
the trick is
something
that
like
you divide it by 0 at some step.
I don't know the answer to that.
Okay.
No, I'll look after this, but. Yeah, that's a good question. What was the other question?
I was just wondering how it handled differentials and,
Let me,
dy dx.
let's. Where am I? Right, how? I don't know. It's a good question. I'll look. In a second, let me see if anyone else has questions before I go down a rabbit hole for that.
Okay, I've got the dumb question.
Oh,
Oh, I'm sorry.
Oh, so, how do you know if you put something that is wrong, like Lean gives you like a message or something, if you put something like 1 = 2 by L, R, L.
yeah, I mean, let me. Say, yeah, so let's do something similar to what we did before. But let's just say. So, yeah, let's just. Let's just. Yeah, I mean, so we can see here until we get to that step, we have just like normal. But our tactics can and will fail, if we don't see. If it doesn't see what it's expecting, so we can see here that, like, when we use the RFL tactic, it actually is checking that the left-hand side. There's no way it can expand any definitions or anything to make it equal to the right.
So Lean is not saying that 1 is not equal to 2. Lean is saying that this is not the proof.
It's saying that this tactic, you can't use it here, is what this error message means. Is that like a satisfying answer?
So it doesn't say that, no, this is false. It says, no, this is not the way to do that, right?
Yeah,
So maybe.
Oh, so I missed the first 5 minutes of your talk, but does this support like any kind of proof by contradiction at all, or is it all constructive proof?
yeah, so I mean, there is a. I'm not gonna lie, I'm not very good at this still, this is something I'm still learning. But. I'm pretty certain there is a tactic you can use to kind of construct a contradiction, like if I wanna do, it's a good one for. I had it and I deleted it, so I didn't finish it. Do I have it? I don't have it. like if I have something, do I have my tactic? Like there's a tactic for doing contraposition, that'll kind of take your hypotheses and your goal, flip them around and negate both of them. So if I had something useful here, we would see that, you know, this goal becomes my hypothesis, and it says 1 not equals 2, and yeah, I'll try. I had a code example for that, but I misplaced it. There are, so yeah, I mean, there's a lot of built-in tactics for doing things. That's probably one of them that exists that we could find. Does that answer your question?
Yeah, I guess my second question is, this is like an open source thing, right? So like any mathematician can come by and program something up, you know, in their field or whatever. How can they test, like if they define something or do something, how can they test what they define is what they're actually thinking of? Like maybe they make a small programming error somewhere. Does this have any kind of way to do unit testing or any kind of testing of the correctness?
So the question is like, how do I make sure that what I've defined in Lean is what I
Like what
have
you truly
defined,
want?
what,
Yeah.
I don't know. I'm sorry, that's been my answer to like all of the questions.
Oh, that's
But-
fine.
Yeah, I'm not sure. That's an interesting thought, but
It'd be bad if someone defines something and then they go make a proof off of it that's incorrect, you know?
yeah, no, I see. What you're coming from, I'm just not sure.
Happens offline, what else?
That's true. Anyone else? have a question?
Yes, I've got a pedestrian. So if I wanted to be an enthusiast and
Okay.
play around with this, do you recommend the Lean community or this eGraphs or?
So like if you wanted to learn it,
Yeah, just play around with it, try to
that's
learn it.
just this is where I would start. This is probably the best. It just takes you through a bunch of different, like, it takes you through a bunch
Did you
of
link
different.
up the Lean community or?
Yeah, so this is some, I don't know, somewhere in Germany, some university, someone built this, somebody. This is linked somewhere, I don't know, let me. Yeah. So if you go here and you go learning resources. It talks about that here, there's also some other tutorials that I didn't mention. 'Cause I-
So the good place to start is the Lean community and just kind of look for their.
Yeah, this is good. You can also see there's books. These are the two I mentioned. This one is nasty. Don't trust it. It sounds good, but it's not. Yeah, this has a lot of different resources that we can start.
Things that seems daunting about this is, take any textbook, there's gonna be an online errata with like 100 mistakes on it. And you know, this is like hundreds and hundreds of textbooks and you know, mistakes there, you know, the textbook, you know that they flipped the sign or something, but in here, it's gonna filter it through. It just seems like it's this house of cards.
What do you, one more time?
Well, like any textbook that's published, you
Right.
go online, there's an errata of like 100 typos.
Mhm.
And, you know, many of those, it's pretty obvious that they dropped a negative sign. But, you know, this has like textbooks worth of stuff built into it, and I'm sure there's hundreds of typos that are in there that.
In the early nineties, I saw a calculus book. Where in the first 6 pages, they do pre-calc stuff before they get going. And they got the triangle inequality wrong. And that study survived 6 editions. Yeah.
I didn't have an online errata, like.
Yeah.
There's. The triangle inequality there. I think, yeah, I think part
The
of what,
absolute value of X plus Y is less centered, the absolute value of X plus or minus the absolute value of Y. So I mean, they must have done bad.
Right. I think part of what I guess mitigates that is that if it was proprietary, that would be a lot scarier, I feel, but this is open source and. And we, in a sense, I guess there kind of is, we are on a list, it's just, you go to GitHub and you open an issue and you complain and you ask somebody to fix it. But like, I see what you mean, like, it could be more of an issue if you had like somebody do something wrong and it pops up in Matplotlib, but. I guess I think that's more of a human issue than the language itself, and I think there are a lot of steps that. This and most open source projects go through to mitigate that.
Other questions? Well, I think you get the question session trophy. All right, let's thank Hazel.
Yeah. Oh, Oh, I wasn't looking at the Zoom chat, I'm so sorry.
Like you choose screen that's small.
Right, like you're. I can't.
I'll stop.
There you go. I go there.